Thank you. Thank you very much for inviting me here, and thank you for placing me right after Wouter, because this essentially saved me the 5 minutes introduction to what the whole idea of this project is, and I can start really with the meat a little bit. So lots of the motives we've seen in the talk before will actually resurface here, both in terms of what it needs to trust the proof assistant and in terms of all the issues with extraction we have seen before. So I'm Yannick Foster. I'm a member of the Galimet team at INRIA Nantes, and this talk is placed in the setting of the MetaCoq project. So all of that is work with the MetaCoq team. I'm going to mention their names again a little bit later. And I wanted to start with motivating all the many beautiful things that have been done in proof assistance in the last years to actually get to the point, what can you trust in Coq? I'm skipping the motivation a little bit because I don't want to repeat too many things that have been said before. The question is, what do you have to trust in order to believe that the result you just verified in your nice proof assistant is actually true? And apart from all the things we have heard, the specification has to be correct, and so on and so on, one of the things was the proof assistant has to be correct. And a lot of time I want to spend today on the question, what does it actually mean to say, okay, your proof assistant is correct? What do you have to trust here exactly? And one thing you have to trust there is the underlying theory. In Coq's case, and I'm mainly going to focus on the Coq proof assistant today. In Coq's case, that's the calculus of inductive constructions and a very specific variant of the calculus of inductive constructions that's implemented. And the other thing you have to trust is you have to trust that actually the implementation gets the underlying theory right. And it really does that. Really, you don't care totally about all parts of the implementation. What you care about is that the small core, the kernel of your type and proof checker, that this bit is correct. Because if this isn't correct, there's no hope that you can actually trust code. I want to start a bit with talking about the underlying foundation and the type theory. What exactly do we have to trust there if we want to trust Coq? Here are a couple of screenshots from the Coq reference manual. They're just rules. And then there's a lot of prose trying to detail and explain all of the type theory. In the end, of course, due to the prose, that ends up to be not fully formal, but let's say semi-formal. Still, there are various things which are just plainly left out because they are not clear enough to be specified even in prose. And the only specification of these things you can find will really be in the OCaml code written in the Coq kernel. You can also read all of the papers and the many PhD theses that have been written over the years to develop Coq. And usually all of these papers or theses covers one often then new aspect while disregarding other aspects, in the sense that, let's say, they prove soundness of the new theory with a new feature added, but then they don't actually consider the calculus of inductive constructions with all of the possible features because that just makes the proof more cumbersome. In the end, we end up in the case that there's not really a uniform presentation of the calculus we want to look at in papers, and there is not really a proof for a type theory with all aspects. One thing that we see, for instance, that there are different approaches to consistency. Some papers introducing extensions to Coq's type theory and consequently to Coq do prove consistency via strong normalization. Some others provide set theoretic models. Both are perfectly valid ways of proving consistency. But if you have a proof of consistency via strong normalization for the one feature on top of CIC and a proof of consistency via set theoretic models with another feature on top of CIC, merging them into a consistency proof of both features is going to be extremely hard, because either you have to transport a strong normalization proof to be a set theoretic proof or the other way around. And then the other bit you have to trust is the implementation, and that also means a couple of things. What does it mean to trust the implementation, and what exactly has to be trusted? This is kind of a picture you might see in an introduction to proof assistance course where the ideal is explained as you have all of this untrusted code, which might be type inference or tactics or plugins, or say implementation of type classes. All of these things are allowed to be wrong in order for the whole thing to still work. If a tactic occasionally fails, that's fine. And then there's the trusted code base. This contains things like parsing, like type checking, like extraction. If they are wrong, there's not really any hope to trust the result anymore. And type checking is exactly this bit that's called the kernel in lots of proof assistants, where really the proofs are checked already after parsing. I was hoping that we can, yep, that seems to work. We can actually look in the COQ repository to have a quick look at the implementation. And one thing I want to point out is that the repository contains in total 730 lines of code. Now, of course, not all of these lines of code are crucial. Not all of them belong to the kernel. But still, in order of magnitude, this gives you an idea that there's quite a bit of things involved if we say that the implementation gets it right. I think about half of this is just COQ code, so half of it is OCaml code. Still, we're looking at 350,000 lines, something like that, of OCaml code. A thing the COQ developers do here is to maintain a file of all the critical bugs that COQ has seen in the years since it is around, which are quite many years. And they usually write when this bug was introduced, how long this bug affected COQ, well, they don't always write this, but what the risk is that this bug can be exploited by a user. And then this is a long file. I'm not going to the end, but this is a long file. As I said, COQ is an old system. And if you just look at the core, you don't have hundreds of thousands of lines, but you have order of magnitude 20,000 lines of code. And in these 20,000 lines of code, in the really critical part, we have, if we do a bit of division by the bugs in this file, around one critical bug per year. That's again an order of magnitude. Maybe it's 1.5 to 2 critical bugs per year, but it's around this number. And I would, similar to Walter before, say that's kind of fine. Usually these bugs don't actually appear in real proofs. As far as I know, nobody has ever accidentally used a proof of false in proving something they were interested in. But still, as COQ progresses and is developed more and more, we have to ask the question, how can we at least maintain this frequency or maybe even improve this frequency? We don't really want 100 critical bugs per year. We don't really want 10 per year. One, we can empirically say we can deal with. And we can just observe here that due to this complex system, now changing the trusted core, doing kernel development of COQ, and it's similar for other proof assistants, requires at least a PhD in type theory, because there are lots and lots of things going on and very, very good programming skills. The amount of people that have both is not incredibly high, and just coming as an outsider and proposing new extensions to COQ's kernel will probably not get them integrated, because it's not easy to argue that your new complicated OCaml code is actually correct with respect to some theory that might or might not be properly specified. And MetaCoq is on many of the levels that I have mentioned here, that have been mentioned in the talk before, trying to improve the situation. MetaCoq is aiming at giving a new kernel to COQ, implementing a new kernel to COQ, which is verified in COQ itself. And as part of the project, there are many layers and many aspects. The lowest layer is that we give a formal specification of COQ's type theory in COQ. So no semi-formal prose, no left out details. Everything has to be spelled out in terms of the logic of COQ. And that's kind of akin to a formalization of some kind of lambda calculus that you would see in the introduction to lambda calculus. Then we have a whole platform of verifiable meta programming where tactics and commands can be implemented in COQ's functional programming language with some interfacing with this formal specification and some meta-programming tools, rather than as OCaml programs as it is nowadays. Then we do lots of meta theory of Coq, formalized in Coq, on top of the formal specification. We have a verified sound and complete type checker for the formalized type theory. We have verified type and proof erasure, which is the first part of extraction to Coq. And we have an almost verified extraction to OCaml. There are bits and pieces missing, but it's reasonable to hope to have one concrete statement that I'm going to talk about at the end of this talk about extraction to OCaml, that you can actually then trust, then you can give this trust to extracted programs. As I said, MetaCoq is a big team effort. The core MetaCoq team consists of Abhishek Anand, Daniel Alenkov, Simon Boulier, Cyril Cohen, me, Maven Lennon-Bertrand, Kenji Maillard, Gregory Maleka, Jakob Botsch-Nielsen, Mathieu Sozo, Nicolas Tabarot, and Theo Winterhalter. Then we have 20 more contributors. In the last time, we had lots of contributions by Pierre-Marie Pedro and other Coq developers when they try to keep MetaCoq up to date with the current system Coq, by Jason Gross, by Marcel Ulrich, by Jan Leray, and Loic Puget, and Yijian Tang. MetaCoq goes back to 2014, when it was started as template Coq, as a meta-programming framework for Coq by Gregory Maleka in his PhD thesis. It's developed as a joint progress by an ever-growing team since 2017. So we are on this stuff for around and a little bit more than 5 years now. I will try to give a little demo here, and I hope this is not a mistake. So I have to switch the window I am sharing, and it seems like you can now see this other window. Yes, that looks good. And I'm in the Coq buffer now, where I have imported all of the necessary libraries.
Can you maybe increase the font size?
Yes, of course. How about this?
It's okay, so it shows up as square for us. I think the window.
Yeah, let's try this.
Okay, that's much better.
Okay, great. So I give you, oh no, maybe that's a little bit different. So this should still work for me and for you. And the first thing I want to show you is and again, let's make this bigger. I want to show you the formalization of Coq's syntax as an inductive type in Coq. This is more or less a literal copy of the OCaml data type representing Coq syntax in the kernel. You have a constructor for the Brown variables, the Brown indices. You have a constructor for lambdas, something for application. These are constructors. This is the case analysis construct called match in Coq. Here are fixed points. Here are primitive integers, primitive floats. All of the things you can have in a term in Coq are reified into this inductive structure. And then we actually have commands implemented in Coq that can go from a MetaCoq term, which is the identity of natural numbers, and give you its syntactic representation in this inductive data type. So the identity of natural numbers is a lambda, which has a named binder named x of type. It is an inductive type placed in this path in the global environment, which is called nat. It's the 0th inductive type in this mutual inductive block, but natural numbers are not mutually inductive. And then the body of the lambda is just the variable 0. Similarly, we can go the other way. We can write a definition in this reified language for terms and say, go the other way, please unquote this definition for us. And if we quote this, this is the constructor 0, because it says exactly this is the constructor of the 0th block in the mutual inductive natural numbers, but there is only one. And then it's the 0th constructor in there. So it will be the number 0. If I put 1 here, everything should still work, and I get the constructor S, so the next constructor of natural numbers. All right. Let's go back. Let's go back to the other window. It seems to be working, great. And let's talk about all of the things we prove. I've shown you the type of syntax, and we define an inductively defined typing judgment, a proposition on this type of syntax. as you would if you would say define system F in Coq, or maybe the characters of the constructions in Coq, or these kinds of things. In the end, it's just a lambda calculus. We define conversion for it, we define the typing judgment, and then we prove all of the things you would expect to be proved about a lambda calculus if you do it in Coq. So we prove weakening for context, we prove substitutivity of typing, confluence, subject reduction, validity, which states that the types of terms are typable. So if T has type A, then A for sure is also well typed. We prove canonicity, meaning that the weak head normal form of a term of inductive type starts with the constructor. We prove consistency, assuming strong normalization of the reduction relation. In the end, there's no hope of really proving consistency of Coq in Coq, because that's not going to work due to circularity issues that also arise in Gödel's incompleteness theorem. And then we prove weak call by value standardization for first order inductives, which is the longest thing here, and maybe the least flashy thing here, but it's very crucial for extraction. And I'm going to talk about it a little bit more. The theorem states that if T is of first order inductive type and it is convertible to an irreducible term V, then T weak call by value evaluates to V. So if it is convertible using any of the many mechanisms you have for conversion in Coq to a term to a value, then actually you can use weak call by value evaluation to go to V. If the thing is of first order inductive type, natural numbers are first order inductive type, lists over natural numbers are first order inductive type. We just don't want higher order features or proofs to be. And then, maybe don't read the full slide yet. I had to prove this theorem a while ago, and my first attempt was, well, I started reading some books and some papers on how to do that. And there are several methods on how to do that, and there are several methods described in lambda calculus theory and type theory. For instance, one based on parallel reduction. But then I ran into a problem that we run into quite frequently in this work, and this work is about the different types of truth we have in proof engineering, in giving proofs in the context of the MetaCoq project. So for sure I knew that the theorem I wanted to prove is true. That's good, but in the context of formal proofs, that's never enough. The second type of truth that you can see is that there is a proof of this theorem, and still I had a proof of this theorem. I was looking at a paper, I think by Carl Freire, who proved a similar property for a similar system. But still, that's not really enough, because we want to have that the proof of this theorem can be formalized, can be machine checked in a proof assistant. And I was confident that I can formalize the theorem. The problem was that actually what we really need is the fourth type of truth here. The fourth type of truth says that the proof of this theorem can be formalized in less than a week, or maybe less than a month, or maybe even less than a year. But if we don't have a reasonable amount of evidence that actually starting the formalization of this theorem will terminate in reasonable time, it's not really a good use of my time. And the problem is that distinguishing between 2, 3, and 4 needs a lot of experience. And we very frequently get this wrong, and our estimates how long things will take are usually wrong, not because we don't trust the thing we want to prove, not because there are not many proofs out there, but because it's very hard to estimate how long such a formal proof actually takes. So what I did here for this weak call by value standardization thing, I used the trick that we use all the time. In the end, we don't actually care that much about weak call by value standardization. It's an auxiliary result that you need somewhere in the theory of extracting from Coq to OCaml. So what I did is I strengthened the assumptions of the theorem. Then it is still true, and these assumptions are not necessary to get a proof, but they are very good to get a simple proof. The simple proof goes as follows. Due to strong normalization, every term has a weak call by value normal form. And then we can observe that weak call by value normal forms of first order type are irreducible. And then you have this thing V here, and this weak call by value normal form, say V prime that you got here. And using confluence, they are the same. So actually the result holds using strong normalization of conversion, which is not necessary to get the proof, but actually makes the proof a lot easier if you want to do it properly. A couple of more words about consistency and strong normalization. What is implemented here and what exactly do we assume? So one thing that is implemented is something that also came up in a talk before, at this fixed point d to d of say lambda calculus terms. And the problem there was that this was not a strictly positive inductive type, which can lead to inconsistency. In MetaCoq, we have implemented a strict positivity checker for inductive types, so that's not going to lead to a problem. And the second thing that's crucial is the guard condition for fixed points, which ensures that fixed points, that recursive functions, are always terminated. This one we just assume as a syntactic oracle, as a Boolean function, and we assume that it must be that it is preserved by reduction and substitution, and that it is implemented in such a way that it ensures strong normalization. So we abstract away and we build the theory and everything we do in MetaCoq for every possible implementation of the guard condition that you can give. Coq gives one of these conditions, and we orthogonalize out this issue of normalization and of consistency from the meta theory and from the correctness of the tools that I come to in a minute. It's future web, though, to actually talk more about the guard condition, to specify the guard condition, which currently really only exists as the OCaml code defining it, to specify it more logically, more abstractly, then to implement it as a Coq function in MetaCoq, and then maybe reduce it a little bit to some simpler conditions, to give a transformation of Coq's type theory as implemented in MetaCoq with the guard condition as implemented in Coq today, to another type theory where the guard condition is a little bit more strict and a little bit more trustworthy, and then maybe have a chain of reductions ending at a guard condition, which is very natural from a type theory perspective. Now we have all of this meta theory in Coq, and what we do on top of this is we implement a sound and complete type checker. The implementation in the soundness proof were in Theo Winterhalter's PhD thesis about 2 years ago now, and then a re-implementation of this based on bidirectional typing and a completeness proof are in Mabel Leonard Bertrand's PhD thesis, which was handed in a couple of weeks ago. And this now gives us a real type checking function, the thing that's happening in Coq's kernel. And we have proved that it is sound with respect to the specification we have given and complete with respect to the specification is given. We don't talk about complexity and about runtime, and actually it's a little bit slow. It's okay, you can run it on small examples, you can't run it on big examples, but the vision here is something like, we don't really want to replace the kernel of Coq, but we would like to have a verified kernel which you can maybe run once a week on your very fast cluster of machines, or maybe even once a month, to check that you did not actually use any problematic parts of Coq's kernel, and then your daily life is still as fast as before. The kernel gives you fast answers, produces proofs and checks proofs quickly, but you have this MetaCoq verified kernel that you can use as the ultimate checker to ensure that what you're doing is actually okay. Here we have a little success story that hints at how I would say MetaCoq can be a tool to prevent future unsoundness in Coq. So when Maven was proving completeness of MetaCoq's verified type checker, he noticed that type checking a well-typed case analysis on cumulative inductive types can go wrong. In particular, what can happen is that this term, which does a case analysis on a cumulative inductive, an element of a cumulative inductive type, is perfectly well typed, but still MetaCoq's verified type checker will say this is not well typed. And the problem there was that branches are represented as lambdas. So when you do a case analysis, you have the variables for a branch. They were not represented just as the names or something like this. They were represented as lambdas in lambda calculus, more akin to recursors than to a real case analysis construct. And actually, even Coq's type checker had this problem. Coq's type checker would say no to a perfectly well-typed term. And then Mathieu Sozo noticed that this issue can actually be turned into a subject reduction issue in Coq's kernel. This was not a consistency issue. This was not severe. No proof of faults was around. But still, subject reduction being broken is something you don't really want. And Mathieu provided quickly a let's say, a quick and dirty fix in Coq's kernel. But this was very hard to formalize for Maven because it required strengthening. So the opposite, the other direction of weakening, where you drop a couple of things from your context. And if you drop in the right way, you can still obtain the same type. And then what actually became the solution was an idea by Hugo Hermelin, which was then implemented by Pierre-Marie Pedro. And the idea was to represent branches with a name context, like you see it in the user interface syntax, like you would have actually maybe expected it to be implemented anyways, and the body. Then that was the new solution in Coq. We adapted this in MetaCoq, and mainly Mathieu worked on this for about a year. That's maybe an example where our estimate how long things take went slightly wrong. Nobody actually expected this to take a year, but MetaCoq has by now a big code base of many, many proofs, and they had to be adapted to this new representation of cases. After that was done, Maven was able relatively quickly to prove completeness of the type checker and to prove strengthening of the theory based on bidirectional type checking. And this was actually an example how trying to prove something in MetaCoq about Coq led to finding a problem in Coq, a completeness problem, but still a problem, fixing the problem in Coq, bringing the fix back to MetaCoq, and proving that now the issue is actually gone and everything is fine. In order for this to work all the time, and in order for especially MetaCoq's verified kernel to be able to replace maybe Coq's kernel, we need more features than we currently have. We need to cover all of the type theory in Coq, which we currently don't do. So one thing we don't have is eta conversion. The fact that yes, this should read fun x. So the fact that lambda x, f of x, is actually convertible to f if x does not occur in f. We don't have this at all. We don't tackle eta in MetaCoq at the moment. The problem is that we don't know how to prove either soundness or completeness, depending on how you implement that, of the type checker, but we are on that. Then Coq has template polymorphism, where I say a list of natural numbers can both be set, which is the lowest thing on the universe hierarchy, and it can be, if you do something like this, it can be at type at level I. Coq has a module system, which is used heavily in not only the standard library, but also the standard library, which we don't specify at the moment. But this is very active work in progress currently by one of our interns, and we hope to soon have a story about the module system. Once we have all of these things, we can more or less type check arbitrary Coq programs given enough. So the vision here is kind of that in the future, if somebody comes and wants to give a new extension to Coq's type theory, implement a new feature, the idea would be that first they maybe can extend the formalized type theory in MetaCoq, verify that all the meta-theoretic properties that you want to have, kind of as a sanity check, are still there, on top of everything that's there. So this should not be incredibly much work. Then extend and verify the aspects of the type checker that we have in MetaCoq. And only once this is done, and we have created evidence that this extension makes sense, extend Coq's kernel. Of course, there's still no formal correspondence between Coq's kernel and the kernel given in MetaCoq. But as I said, once a week, maybe you can run MetaCoq's kernel to ensure that everything is fine. And now I want to use the rest of my time, so something like 5, 6, 7 minutes, to talk about extraction in Coq. Extraction in Coq is this tool that you can use to turn a Coq file, a .v file, into an ML file, an OCaml file. This extraction goes via an untyped lambda calculus called lambda box. The lambda hints at the fact that it's really a lambda calculus. The syntax is more or less the same syntax that I showed you before. The box is the replacement that we put for things that were erased, for proofs and for types, because OCaml does not have first-class types. And then it also generates an MLI file explaining what the types of these extracted things in OCaml are supposed to be. And then you can use the OCaml compiler to produce something executable. All of this was first implemented and theoretically presented in Pierre Letouzy's PhD thesis about more than 18 years ago. So extraction is turned 18 this year. It's one of the central claims to fame of Coq, not least because actually compsert, the verified compiler from C to assembly that was verified in Coq crucially depends on the extraction, because it is a program written in Coq but extracted to OCaml to actually execute. And there are a couple of issues of today's implementation of extraction in Coq. The first one is that it has bugs. Sometimes it produces not well-typed code. We know all of these bugs and we know how to write patch files to kind of fix the produced code, but it's a bit annoying. These bugs are currently not fixed, and they cannot really be fixed because strategically we can observe that that extraction in Coq is unmaintained. The initial developer has moved on and is working on other things now, and the code base is not really understood by anybody currently. Then there's a conceptual issue as well, namely that Coq's extraction inserts lots of opt.magic at points where Coq's type theory, which is dependent, very expressive type theory, cannot actually be mapped to what's happening in OCaml, because OCaml is by far not as, the type system is by far not as expressive. And then there are a couple of missing features. For instance, we cannot really target OCaml with GADTs, which would, however, remove lots of opt.magic. And currently, it's not really possible to add these features to the extraction code because, as I said, it's not really maintained. So the vision here is we want to give a verified implementation of extraction. Just rewrite the whole thing again as a Coq program. We start by formalizing Coq in Coq. All of that is already done in the MetaCoq project. Then we formalize a variant of OCaml, so formalize the semantics of a variant of OCaml, re-implement the extraction, and verify that it behaves correctly. I want to start by talking about what I mean by OCaml here, because there is no formal semantics of OCaml in Coq, and proving, just giving one, and then proving that our extraction behaves in the right way might not be completely trustworthy and might be actually a source of unsoundness, because it's hard to get the OCaml semantics formally correct, because again, it's given a lot in prose in, say, the OCaml map. So what we do instead is we use the Malfunction project by Stephen Dolan. This gives a nice syntax for lambda, the intermediate language of the OCaml compiler, and it gives an interpreter function for lambda written as an OCaml program. And now that's better than a semi-formal specification, because an OCaml program is something that's reasonably formal, and where we can have some hope that we can transport one OCaml program into something formal in Coq. So what Stephen does is he has this type of malfunction syntax, of the lambda syntax of the intermediate language. And what we do is we just translate this into an inductive type in Coq, and then we work on that. And then we have to get the formal semantics over. So currently, malfunction is specified using an interpreter written in OCaml, using references to tie the knot for recursion. So the first thing we do is we make the malfunction interpreter pure, still as an OCaml function, but no recursion, no references anymore. We implement recursion instead via letrec, and then we just test with lots of unit tests, lots of OCaml programs in this interpreter that actually we didn't break anything. We could actually also imagine proving that these two programs are correct, but again, this would require a formal semantics of OCaml. Or some program logic for OCaml, as it is maybe already possible to use in projects like CFML or Iris. And then, but still, here we rely on testing, and we have lots of evidence that you can actually even look at the thing that they're doing the right thing. And then we implement the interpreter in Coq again, just disabling guardedness checking for a moment, because of course this interpreter is not going to be structurally recursive. We can extract this program, we can test again, then we have 3 interpreters doing the right thing. And then we define an inductive evaluation relation, as you would do it when you do lambda calculus theory, and prove that this is actually included in the relation that's induced by the interpreter. Then we have good evidence that we have captured the semantics of the intermediate language of the OCaml compiler correctly, and we can now use this as a target for our extraction program. So what we do is we go via untyped lambda characters to an MLF file, to a Malfunction file, and then use the OCaml compiler and the Malfunction compiler, the OCaml toolchain, to still go to an executable as before. When we do the proof, we are currently doing the proof, and we encountered lots of subtleties that are kind of covered in Pierre-Létousy's thesis, but sometimes not. And these subtleties are between the different semantics that you have in Coq and in OCaml. So Coq has a structural fix. By this I mean that a fixed point has one structural argument. This can be argument number 7. This is the one that has to become structurally smaller, and the fixed point application will only reduce once the structural argument is there and has reduced to a constructor. In OCaml, that's not the case. Letrec is unary. Once the first thing has reduced, the fixed point is going to 5. Coq has higher order constructors. That means you can write cons, just like that. And it's going to be taken as a higher order function, which will produce a list if it's given 2 or 3 more arguments. In OCaml, constructors are blocks. Writing cons does not make sense. You have to apply it to 2 things. If you want to have the higher order thing, you have to write lambda xl x cons l. In Coq and in lambda box, this intermediate untyped language, you can do a match on a box. This is because in Coq you can do a match on a proof, the case analysis on a proof, because proofs are terms, are programs. And the box is going to be implemented as some kind of its argument eating fixed point in OCaml, meaning the match on a box will be translated to a match on a function, which will lead to a segfault, to an actual issue. Then we have the Brown indices in the specification of everything in Coq and MetaCoq and lambda box, and we have everything in a named word in OCaml and Malfunction. And lastly, the bit that's complementing the fix is the match. And in lambda, the intermediate language of the OCaml compiler, and in Malfunction, these are switch and projection instead. So what we do, I'm not actually explaining this whole graphics to you. So what we do is we have 8, 9, 10 syntax transformations, and in all of these transformations we take care of one of these differences. So let's say here we have a version of untyped lambda box which has unary fixes, higher order constructors, and matches in box, and then we go to a version of untyped lambda box which has no parameters, which will be better for efficiency. And then we go to a version which has everything the same, but does not perform matches and boxes, because we do program transformations to actually allow this. And then in the end, we ended something that we can easily translate to Malfunction. And then we have a proof that every Coq program that we call by value evaluates to a value, and you can use with a standardization as before to plug this together with arbitrary conversion. Then actually the Malfunction program will go to the same value. All right, we get a couple of free results here. So one thing is that the 30 Coq project, which is verified extraction from Coq to C, can benefit from our transformations, and it's now very close to getting a final QED. And we can do another thing, namely that if we have the semantics of KCML in Coq, which also doesn't exist, we also get operationally correct extraction to KCML pretty quickly, because we just have to do the same thing we did for Malfunction. After all of the passes on lambda box, the lambda box to KCML translation will be relatively quick. Okay. So what do we need to do in order to kind of fulfill this vision? Both this vision of having MetaCoq entangled into the extension and development process of Coq, and of having a verified kernel that you can run, say, once a week, where we have proof based on MetaCoq that this is correct, and of replacing the full extraction mechanism by what we have here. What do we need for this to work? So first, in Coq, we would like to replace template polymorphism with something more general and theoretically nice, but also practical, like some kind of sort polymorphism. In MetaCoq, we need to specify eta conversion and adapt and proof correct the checker. We want modules, and we are working on that. We would like to specify primitive integers, floats, and arrays. Currently, we just have them syntactically. We don't specify anything about reduction. We want to talk about conversion machines, things like native compute, VM compute, and so on. Currently, we don't cover that at all. And for extraction, we want to add semantic typing. This way, we can say that we can prove actually that our result will behave like a certain program with a certain OCaml type. That's very important because, as Wouter has as discussed, if you call your extracted program from some OCaml context, you have to make sure that these things match. And this here will actually allow us to give a precise specification of what happens if you call a coq function from an OCaml content. And the preconditions of this theorem will formally rule out things like the safe head function applied to the empty list. So at least we have a formal way, a readable formal way of saying, okay, this is exactly what you have. This is the guarantee. And if you do something else, it's not going to work. We want to add axioms on the coq side, which can then be instantiated using OCaml functions. So interface in the other direction, call OCaml functions from coq code, which will amount to some kind of realizability semantics for lambda box and coq types. We want to have the extract inductive and the extract constant commands that we've seen in the last talk, where the true and the false constructor were mixed up. And again, at least say what has to be the case formally for them to work out. That still doesn't mean that users do use them in the wrong way, but at least there's a clear machine-checked formal specification of how they have to be used. And lastly, we want to implement and verify optimizations of extraction. Currently, coq has 10 of them, and we want to give proofs in MetaCoq that all of them are actually correct. All right. So I'm going to leave you here with our vision regarding the kernel, that we have a verified kernel that can be part of some kind of, say, weekly CI, and our vision regarding abstraction, where we try to prove it correct once and for all, and then everybody can use it actually in their daily life. All right. Thank you very much for your attention, everybody. I'm not sure we'll have much time for questions, but I'll leave that to the session.